So, today we'll talk about conservation of momentum, and so kind of it's a crux activity for this class. We talked about conservation of mass last week. I'll try and put that in context for something that's useful to you briefly this morning. But many of the things that we are relevant in this class, relevant to your programs, and of course the third year is where you stop doing statistics and dynamics and do something that might be actually related to what you might want to do as a career. And we'll talk about, well, this is clearly for energy engineers, or it's how a turbine works. This is a Pelton wheel. It's basically the same as a water wheel that you'd see in for grinding corn rather than generating electricity. A whole bunch of cups. I guess you need to see at the beginning. A whole bunch of cups pointing in the direction of the gas jet, air jet, and the cups catch the air and are moved by it on the spindle and turn linear kinetic energy into rotational kinetic energy. And that's important for us because that's how generators work. A drill, electric motor being the reverse of generator. You spin a coil around inside magnets, you generate electricity. That's how we generate electricity this period. Faraday's law, I guess. So it provides useful work for us. So that's kind of an activity that we might be interested in. So in its simplest form, that is what it is. You've seen this before. Hitting twice, it comes on, but I guess it doesn't play. Perhaps you have to hit it a third time. And you've seen the jet lev before, right? Would I spend $28,000 on it? No. Yeah, fine. So, interesting tool. $28,000 apparently. Interesting. But I guess more of interest to us are the principles. You have this umbilical attached to a pump, which is behind it, and that allows you to pump water at some rate through this yellow umbilical. It comes out of these jets, and you can steer it in some way and play around with it. And I guess later on in the class I'll probably use something that has a whole bunch of these doing like, not gymnastics, but water, synchronized swimming type things, but in the ocean off Catalina Island by the looks of it in California. So that is conservation of momentum. Actually, we did an example, I think, in week 5 when you'd have looked at your videos. It's gone through a block wall. I don't know why it's stopping. Has the connection gone down or something? Yeah, it's gone through the wall. So hence the term the sleeping giant, and hence it being an object of some concern in a lab if you don't treat it properly, because it's charged with a lot of potential energy. It's stored under pressure, under potential energy. Again, this is some guy. Same deal. Don't need that. And I don't know what else you got. Yeah, a bit of fun at work, I'm guessing. And things more fluidy or liquidy, I guess, in terms of what we're doing, is the idea of an undershot weir. And so often you use weirs across rivers. If you look at the upstream level versus the downstream level, it gives you an idea of the flow velocity in the river. So you can get how many cubic feet a second or how many cubic meters a second go through a river just by measuring upstream and downstream pressures. A bit like a Venturi gauge that you measure constriction in a pipe. You measure the pressure at the constriction and the pressure upstream or downstream, and the difference between those gives you a flow rate directly, and actually not so different from a pitot tube on a plane that we've talked about. And so I don't want to go any further with that. And yeah, fine. Don't want that. And the other one, I'm not going to talk about that. So that's our topic for today. And so we'll talk about conservation of momentum, It's really just Newton's second law without energy losses. And so we'll do some examples for that today, one of which we've maybe kind of done already, but just to reiterate. So that's our plan for today. Any questions before we get going? No? Okay, fine. All right, just to recap. So let's go recap what we did before. Then we'll talk about that kind of energy systems that we talked about today. And then we'll use Reynolds transport theorem to be able to write the equations, quite simple equations, for conservation of mass. And so what did we talk about last time? I guess I don't want to do it to death, but you know that last time we said that we are conserving mass. We define an intensive property, which is B per unit mass, which if B is equal to mass, then this is equal to 1. We substituted into this. We said that we're at steady state, so we don't care about this. We said that this value here is equal to 1. This value here is equal to 1. And we ended up with a conservation equation, which was density times rate of change of volume of a control volume plus volume of that control volume times the rate of change of density plus the sum of, I will write it as a velocity W, because we said that it has to be relative to the boundary. So it's the velocity relative to the boundary times density times area, and that equals 0. We defined it on a control volume, and that looked like this. We had an upstream location and a downstream location, and we would have W1 and W2. And we could also write this as this term here was also a mass flow rate, what we called m dot, just these terms together. A velocity times an area gives us Q, so these two together give us what we would call Q, and Q times the density, cubic meters per second times kilograms per cubic meter, gives us a kilograms per second. And so it was kind of a forced fit, because we spent Friday filling up a beaker, which you could do the calculations for without any of this course, just by taking a volume and looking at the volume rate by which it fills to calculate a time to fill. But we solved it using these complicated ways of looking at moving boundaries, etc. So that might become useful for us later. But to perhaps link this to some of your disciplines, if you look at the equations for porous media flow, so if you are a petroleum engineer or an environmental systems engineer or an energy engineer or a mining engineer, you all look at flows in porous media. And surprisingly, not surprisingly, we could perhaps illuminate that behavior of the equations that you'll use. In environmental systems engineers, do you take GSci 452 this semester? Is that Rachel Houseco teaching it? Who's teaching it? Parzak, Byron. Tall guy, great guy. Had been in class 20 years ago. Perhaps more. And his now wife. Yeah, Baron, Parzak. So this is our coordinate system. And so if we take this expression here, we could write this in terms of our coordinate system as V1, V2, ouch, and I should stop using my thumbs on this. And this would be dy, this would be dx, and this would be dz. And so we could take this expression here, and we could write density times rate of change of volume plus volume times rate of change of density plus, how am I going to write this? I'm going to write this as V2. Rho A equals 0. So all I'm doing is writing this out in longhand. And so what we could do is we could write this out. Let's say that the density of water flowing in our system doesn't change. But let's say that the volume of our control volume might expand slightly. So we could write this as density times the rate of change of volume plus, let's write this as delta V over something. Density. The area of flow is dy dz. I'm leaving a space. And I'm going to write, add to both sides, I'm going to multiply by 1. Whoops. And so this happens to be the continuity equation written in a differential form, which just says, if I write it out, the density times the rate of change of volume plus dv dx times volume, this is a velocity in the x direction, equals 0. And so this is a generic conservation of equation, conservation of mass equation written in differential form, where we've just chosen the control volume to be a little differential cube. And so environmental systems engineers or petroleum engineers wouldn't do that. They would look at forcing fluid through a core. They would apply an upstream pressure and a downstream pressure, so P1, P2. There would be a velocity downstream and a velocity upstream. And if you ran this experiment and measured the velocity as a function of pressures, you'd get Darcy's law. And so you'd write Darcy's law as the velocity that flow goes through a core of material as equal to the hydraulic conductivity times the gradient of head. And head is just equal to elevation plus pressure over unit weight plus v squared over 2g. Might recognize that. And we always assume that in groundwater flow velocities are small, so you throw away that term. And so this would just be the pressures at these points, but also the elevations of those points above a datum that you choose, right? Z equals 0, so this is Z. And petroleum engineers would write it in terms of same equation, but velocity is equal to permeability, units of meters per second, length over length, so velocity, units of meters squared, strange units, but they're related to the size, the diameters of the pores. Doesn't matter what these terms are. This is viscosity that we've talked about, and a pressure gradient. And for each of these expressions, this is just to give you some context of where you might be going, we could substitute this term in here, and we'd get something that looked like rho d v dt plus d2 dx squared times permeability times head equals 0. And if you're a petroleum engineer, it would look something like Same thing on the left-hand side, plus K over mu d2p dx squared. 0. Groundwater flow equation, the idea being that if you have a well and you want to flow water into it, or it could be a petroleum well for that matter, then the drawdown that you get as water flows towards that well, you can think of as dH dx. So this gradient either of pressure, I guess this term here would be operated on by the differential, is just where it comes. So very strangely actually, the groundwater equations, which are talking about having to provide some power to push through some fluid, the mere fact that if on the same cross-sectional area it's coming out, it's requiring a pressure drop between upstream and downstream to push it through, means that you're expending energy. So Darcy's law exactly calculates what that expenditure of energy is by making the fact that you have to have a pressure drop between upstream and downstream to make flow occur. Bernoulli predicts that if you have a pressure upstream and downstream and you have steady flow, the pressure should be exactly the same. You're exchanging things. If it gets constricted, you're changing pressure into velocity, but there's no loss of energy in Bernoulli's equation. So this is directly relating to what you'll do in the final 2 years of your programs, for all of your programs. And so quite surprisingly, conservation of mass seems like a stupid and trivial idea, just mass in equals mass out, and if it doesn't balance, you have some accumulation. This is the accumulation or depletion of water in the reservoir. Change in volume of water with time. Volume times density would be a mass change with time. And so petroleum engineers tend to write it in terms of pressures because pressures influence the phases of different components, and you have to know what those phases are, whether it's a gas or a liquid. And hydrologists tend to work in terms of heads just because you're usually working with water and you don't have to worry about compressibility of the fluid very much. So anyway, that's where you might be interested in. Oh, I put my watch on. I didn't mean to do that, but anyway. Yeah.
So is Darcy's law both the B equation and the H equation, or is it specifically only the H equals equation?
Both. Henri Darcy was an engineer in Dijon in France in the 1800s and wondered how the fountains of Dijon worked. And so he did an experiment to do this basic experiment. And so you could measure either pressures between upstream and downstream, or you could convert those pressures into heads. And if you relate heads to velocity or pressures to velocity, specifically their gradients as you go downstream, then you get a coefficient that links them together. And so these coefficients are different. They're called different things, but this is Darcy's law, just like Ohm's law or...
Follow-up if possible. Well, for the continuity equation in differential form, when we multiplied in the dx, would the dx also be extended to p times v?
dx equals p times...
No, I mean the dx there, would that also multiply to p times v, the other expression?
No, because we've just multiplied it by 1. We've multiplied by dx over dx. So we've multiplied this by dx over dx, but we don't care about this, right? Because this is actually 1. And we multiplied specifically by dx because I wanted to get this as a gradient and this as a volume. Because there's a volume on this side, right? This is the volume times density change. So that's all we did there. Okay. Right. All right. So conservation of momentum. My handwriting's not getting better. All right. Let's see how skillful or not I can be. I'm going to steal this. Let me. No chance, so I don't want that. So I'm just going to use this. So you can write it where you wish. I'm going to go back here and remove my annotations. And I'm going to now note that when we talk about conservation of momentum, which I'll come back for, is it cold season? People getting sick. So what did we talk about? Doesn't want to do that. Oh, it does now. We said that we have this, I'm having a terrible time. We have this quantity B, which before our B was equal to mass, and our lowercase b was equal to B per unit mass, which was equal to 1. And so for conservation of momentum, it's going to be mass times velocity. Velocity is a vector. And B will be the ratio of the two, which will be mass times velocity divided by mass, which is equal to velocity. Velocity is actually a vector, x, y, and z, but let's not worry about that now. So what we're going to do is we're going to substitute this into our Reynolds transport theorem. And for some reason it's grown those terms back. I'm not sure what it's doing. So, actually wait, what for?
Is it possible to use the pen to edit the text? If so, maybe you can click on the equation, copy it, and then you can move it down that way.
I tried to, but it didn't go. It just took the text. I think if we're getting into, I guess I could do this as a screenshot, right? Oh, no, it doesn't. Same. Let's go with that plan A. So all I'm going to do is substitute for this. This was equal to mass times velocity. This is equal to velocity. This is equal to velocity. So, rate of change of mass times velocity. If I just rewrite this by taking the m outside the differential, saying that mass doesn't change, what's this? This is Newton's second law. So this is the inertial term, the acceleration term in Newton's law. So this will be sum of forces are equal to, we are going to assume that this doesn't change with time, so we're just going to assume that this is 0, so we're going to ignore this expression. And we're left then with this other expression, and we're going to write this in terms of what we know. The things that we know, I want to change color. I'm tired of this. We know that density and velocity, so we know that this term plus this term, everything other than this other term, we know that this is sum of mass. And so what we're doing is we're pre-multiplying it by this extra v. So this will just be equal to velocity times mass rate equals 0. So this is our new equation. That's it. So what we've done, instead our term on the left-hand side is no longer 0 as it was before. It's the sum of forces. And I guess we should also realize that this is a vector, fx, fy, fz. This is also vector, vx, vy, vz. But this is a scalar. Mass in or out goes across the boundary. And it's just the sum of velocity, the dot product of velocity and area and density. So that's changed. So I'll write our expression down here. Sum of forces are equal to the sum of velocity times mass flow rate. Yeah. This is a vector. This is a vector. So I guess we could write it as, if we wanted to, fx, fy, fz is equal to vx, vy, vz times the scalar, mass flow rate. And in reality, what we would do is we just take an individual equation. So an individual equation would be, for instance, sum of fx, sum of forces in the x direction are equal to the sum of velocities in the x direction times the mass flow rates, would be one equation. We need to talk about our sign convention. And so it's convenient for us to talk about our sign convention in terms of the things that we've talked about before. We can define coordinate systems. It could be x and y, or it could be x and z. It doesn't really matter. We'd have velocity 1, and we'd have velocity 2. And in terms of what we already know, we've talked about summing momentum. And so if we sum momentum, then this is just equal to density, velocity times area, right? This by definition. Mass flow rate. Sorry, I said momentum. Meant mass flow rate. And we know that mass flow rate in, by convention, is positive. No. Silly me. Mass flow rate out is positive. And our reason for that is that it's a dot product if it wants to behave. And so in other words, when the velocity is aligned with the outward normal, it's positive, same direction. But we also have another term now, and velocity, in this case in the x direction, is in concert with the global frame of reference. So velocity 1 is in the positive x direction, so it's positive. Velocity 2 is in the positive x direction, so it's positive. So we have to be careful with our sign convention when we're doing that. And the reason is that Newton's second law is written in terms of x, y, and z, and so the forces that we reconcile here also have to be reconciled with velocities aligned with the same coordinate system. Likewise, a velocity in the z direction would be positive upwards and negative downwards, but flowing across these boundaries would be the same sign convention. Okay? So, what should we do? Let's do an example. The example's in the book, or taken from the book, but I won't use it. Here's a description of the sign convention. And this is the example we'll do. I won't overprint it on this, I'll just draw it out separately. But the question is, if you have an undershot weir and you're trying to hold back the water behind the gate, is there more force applied on this gate if the gate is down or if the water is flowing underneath? So that's a question that you could ask yourself. And so we now kind of have the tools to deal with that. And so let's do that here. So what have we got? We've got that the sum of forces, let me draw it. So this is our gate. And I'll draw it all the way down first to start off with. And so we are going to define a control volume. And that control volume is going to be my gray thing here. And I was going to write this out. Sum of the forces in the x direction are equal to the velocity in the x direction times the mass flow rate in the out of the system. So if we don't have any velocities in here, right? It's impounded, so there's zero velocity, big container assumption. So what are the forces we have acting on our system? We know if we have a pressure acting on the back, not a velocity, but a pressure. We're going to call this uppercase H, I think. And we'd have a resultant force. You thought you would never use this again, but you were wrong. We don't need to know where it acts because we're not taking moments, but we're just resolving horizontally. So if we resolve this, we have two forces that we want to counter. One would be a reaction in the x direction, which is holding this gate in place. The other is a force in the x direction, which is pushing it. If we look at this equation, we can define what the components would be. Velocity in the x direction and also mass flow in the x direction are zero. Both of them zero. So we're just summing forces in the x direction and setting them equal to zero. And so that would be that the resultant force is equal to the reaction. This is what we want to calculate. Resultant force is equal to what? Fr equals the depth of the centroid, HC gamma area, which is going to be HC is equal to H over 2. Right. Centroid of this is just halfway down it. The unit weight is the unit weight, and the area is going to be H times B into the page. So this has a length into the page. Not to be confused, let's call it W, since we used B previously. Getting too fancy here. Okay? So, and this is going to be equal to R. So it's going to be equal to, bless you, half H squared gamma W. So that's if it's not flowing. That's the easy one. Let's do it if it's flowing. I think I'm going to be fancy. I'm going to save myself some time. Will it allow me to do it? Don't know if it's going to be easier to do. Yeah, it will be easier. So I'm going to erase the gate and draw it differently. To be consistent, I'm going to draw it down here. And I'm going to have some water coming out the bottom. And that water is going to be traveling at a uniform velocity v2, let's call it. And I'm going to try and put in a velocity here, which is v1. We know that it's very tall. Then V1's going from continuity, V1, we know from continuity that V1H has to be equal to V2H. This is the depth downstream. And so V1 would be equal to H over uppercase H V2. And so if we take H much bigger than H, then V1 goes to 0. The big tank assumption, right? And so now all we have to do is be able to sum our forces. So also acting on the outside of this control volume is a force which is acting here in the opposite direction. So if we want to sum our forces, we have sum of forces in the x direction are equal to velocities times mass flow rates. And if we write all of those terms, it would be FR1 minus Rx. So we've got this, and we've got FR2. So those are the sums of the forces acting horizontally. And those have to equal the sum of the velocities. So it would be acting again towards the coordinate system. I guess I should have drawn a coordinate system, right? Been helpful. X, Z doesn't matter, Z or Y doesn't matter. So it's going to be, the equation we have is a velocity. So it's going to be V1 times mass flow rate. Mass flow rate is going to be H times W times V1 times density. And we'll come back and do the sign convention. And we're going to add to that the other one, which is going to be V2 times lowercase h times W. So this is the area, right? Not dividing it by the area, but the area. Times V2, again, times the density, which hasn't changed. So let's worry now about our sign conventions. So we had before that in terms of mass conservation, a mass flow rate in would be negative, and a mass flow rate out would be positive. And in terms of velocities, a velocity in the x direction would be positive, and a velocity in the x direction would be positive. So all this is this, making the case for this. And so that defines what the sign convention is that we apply to our system. Okay? I don't know what that is. Did it last time, right? Yeah, fine. Adds a bit of excitement. So V1 will be positive for what we've talked about. Mass flow rate in will be negative. V2 will be positive. And mass flow rate out will be positive as well. So I'm not adding these, I'm just doing the signs. And so if we want to write it out in longhand, FR1 minus Rx minus FR2 is equal to, this is going to be negative, this is going to be V1 squared plus, and a minus is negative, H W rho. So area times density times velocity is mass flow rate, times another velocity is momentum. Mass flow rate times velocity. This second term is going to be addition, plus plus a plus. So this is going to be V2 squared. Area, which is lowercase h times W, which again is A. I won't leave that there just because it's confusing. And it's multiplied by density. Again, area times density times the velocity is mass flow rate, and multiplied by another velocity is mass flow rate times velocity is momentum change. And so what we could do is, I guess, simplify it. I guess we should realize also that this magnitude here, what is this magnitude here? It's going to be exactly the same as this term here. Half lowercase h squared gamma w, right? This triangular distribution is a resultant force which is acting in the opposite direction, but it's exactly the same. It comes from a free surface at zero pressure. We know that the resultant is the centroid times the area times the density. Location of action is 2/3 of the way down, but we don't care about that because we're just resolving horizontally. So this is going to be a half lowercase h squared gamma times the width. And this is equal to FR2. And so we could calculate what these are. And I guess we're going to go with this as well. Big tank assumption, we lose this. So if we want to write this out in terms of R, I guess if we gather terms, FR1 minus FR2, I'm going to take this term to the other side, plus V1 squared H width times density minus V2 squared. I'm just moving these terms to the other side. Height times width times density equals reaction. So before, we had the reaction in the x direction is just equal to this force. It's a statics problem. Sum of forces equals 0 because there's no accelerations in it. We can't do for this for the second one. So now we have that the reaction, what's holding the gate, is equal to the full FR1, which it was before. So before, when it was static, it was just these two terms. Now that we've lifted the gate, we're changing the reaction by reducing it by a small amount of this force acting upwards. And this is essentially 0. And so we're reducing it also by the velocity that it comes out at, which we can define if we know what that velocity is. And so the moral of the story is that if we want to know whether the reaction that we have to apply to keep the gate in place is larger when it's closed versus it's open, it's clearly larger when it's closed, when it's reacting against this full distribution of pressure, as opposed to reducing it by this amount and also reducing it by an amount which is given by the flow under the gate. So this term is negative, so it reduces the reaction, and this term is negative as well. So it must be smaller. Okay? So that's the kinds of things we do. That's the simplest case that we can attack. All right? Okay. So I won't throw numbers into there because I don't think we need to. So just understanding the fact that if we go back, we have to understand that, one, the expression we have has vectors in it for the forces and the velocities. Those vectors mean that a single equation, if we resolve in the x direction, means that this would be fx and this would be vx, but this would be a scalar which is multiplying it on the surfaces that make sense. The surfaces that make sense in this are into the control volume. This gray rectangle or prism is the control volume, and we have to look at all the forces that are acting on that. They're acting a pressure or on the upstream side and also velocity going into it, and a pressure on the downstream side and a velocity coming out of it, and a reaction to keep this gate in place. I think the hardest part of this class is kind of visualizing what those components are that you ultimately have to solve. And so we then need to remember, once we have this, that there's a sign convention that we can apply. Sign convention is that mass flow rate in is negative, mass flow rate out is positive, but the velocities are in the positive in the direction of the global coordinate systems. And so we can do that. All right? Could stop there, but we could do something else as well. Let's do something else as well. I guess I'm not going to give you the choice. So just also to cement it into what we're doing. We're not doing anything actually any different from what we've done. We started off today with the Pelton wheel, which was this, and we will kind of revisit this idea of a vane that gets moved. And so this vane that gets moved, one of the reasons we're using Reynolds transport theorem is that we did the jet engine problem. And we did it by Bernoulli. And we had that there's a velocity coming out of here, V1, and there's a pressure that we can get here, P2. And we did it with the truck on the apron at San Francisco, and we just wrote that P1 over gamma plus Z1 plus V1 squared over 2G is equal to P2 over gamma plus Z2 plus V2 squared over 2G. We took as atmospheric the pressure where it comes out of the jet engine. We said that we're working at the same elevation, so Z doesn't change. We know that we can get this, and if we get this and we make this equal to 0, then we can calculate what P2 is. So we could write this, if we wanted to, as P2 over gamma equals V1 squared minus V2 squared over 2G. We could multiply by unit weight on both sides. We could multiply by area on both sides. So this would go, and this would be equal to a force, uppercase P2, that's being applied on this thing. And so what we could do is that we now have this as a force, and so if we have P2 uppercase, it's equal to area times unit weight of the fluid. It could be air or it could be water if it's a Pelton wheel. And we have V1 squared minus V2 squared. What we did before was we took the fact that V2 is essentially, we could think of this as the velocity of our control surface. And so if we take the velocity of the control surface as equal to 0, then this term ends up being, let's write it out. Yeah, that's right, VCS and P2. So if the velocity of the control surface is 0, we're holding it, then by definition this is proportional to this term. Let's call this, it's gone off, right? I'm not sure why it does that. It's nothing I'm doing. So let's call this C, and this would be C times V1 squared. If the velocity of the control surface is equal to V1, then this term would be 0, and P2 would be 0. And if the velocity of the control surface was V1 over 2, then this would be equal to V1 squared times 1 minus half squared, which is 3/4. 3/4. Right? And my reason for doing this is that you, and we'll do this next time, we could hold this vane static and it would apply a maximum force. The maximum force when it's static is this. We could allow it to go freely the fastest it can go would be at the velocity of the water, because the water is just getting there and pushing it ahead. And if that's the case, then the pressure that's applied is essentially zero. But the intermediate case is if we hold it in place, and in holding it in place, allowing it to go at some velocity, then there's some pressure that's acting on it, but there's also a velocity it's going through. And so if we plotted here, go and do. This is a strange plot. So if we plot the velocity of the control surface versus the velocity of the control surface, when the velocity of the control surface is zero, this is 1. Right? When the velocity of control surface is 0, the velocity of control surface is 0, etc. When it's 1, it's equal to 1. If you look at the forces that are applied for each of these, so if you look at the magnitude of the pressure at P2, when the velocity of the control surface is 0, it's the maximum pressure. And so it looks like this. Right? When the velocity of the control surface is 0, then the maximum control pressure is this. When the velocity of the control surface is V1, then the pressure force is equal to 0. And at some intermediate value, it's equal to 3 over 4, 0. And this would be equal to, this is V1 squared. And the reason for doing that is relating to our Pelton wheel, and the fact that we want to generate power from it, is if we plot power, which is equal to force times velocity. So force is newtons, velocity is meters per second. Newton meters is a joule per second is a watt. And so the product of velocity of the control surface times its pressure, 0 velocity times a big pressure gives you 0. So this is power. A high velocity times 0 pressure gives you 0. And the products of these two gives you a finite value. And so if you look at the power that comes out of this, it looks something like this. So it has to be going at some velocity and have some resistance to it. So for the Pelton wheel, you attach it to a generator. The coil is spinning inside magnets. If it's static inside the magnets, it generates no power. If the magnets push some force on it that stops it going from its maximum speed. And so if you removed the magnets, it would be fine to go at its maximum speed, but it wouldn't generate any electricity because there's no resistance to it. And so to have power, you can't be going at 0 velocity and having a big force, holding the vane static. You can't be allowing the vane to move at the frontal velocity of the water and applying no resistance, but it has to be an intermediate condition when you're applying resistance to it and it's still traveling at a finite velocity. And so that's kind of where we're going. And so the Pelton wheel that we looked at with the air attaching to it, you could think as this vane, and this vane is just moving on a very big radius rotation arm. This is the vane here, it's going here. As this arm goes to infinity, then that's just translating. It's exactly the same process. And so we'll use this expression again. The idea is that we can look at forces driven by velocities, and we'll look at systems in a bit like this, which are moving, and we'll deal with it in a bit more sophisticated way. And so we'll need to look at our control volumes deforming and moving in that state of affairs. So that's it, I think. Right on 8:50. Let's go.